how can you leverage the idea of polar coordinates and integration to find areas such as the area shaded in pink in this picture? Hello, welcome back to the Quant Plus YouTube channel. Today we're going to be looking at an example of a problem like this. The curves we're going to be working with are r equals cosine of theta and r equals 1/2. The first thing I'm going to do is draw out these two curves. The first curve, r equals cosine theta, has the following graph, and I'm going to be shading it or drawing it in blue. It's a circle with radius of 1/2 centered at the point 1/2, 0. So this is r equals cosine of theta. The second curve is another circle of radius 1/2, now centered at the origin. I'm going to be drawing that in green. This is r equals 1/2. The approach I'll be taking to the problem is thinking about the area contained within the blue circle, and then considering this area, which I'm shading in red, and subtract the red area from the area contained in the blue circle. As for how I'm going to find the red area, I want to find the intersection of the blue and the green point, or blue and the green curve, and use the area formula for polar curves in terms of integration to find this area. And then, based off symmetry, multiply the result by 2. Inherently in doing that, I'm assuming that I'm limiting myself to the first quadrant, and mathematically that is simpler to do. Now, something that can be pointed out immediately is that there is a small region right here that is beyond the intersection point of the two curves, but still of interest to us. So that we're going to have two separate integrals. Step 1, we're going to find the intersection point by setting the two curves equal to each other, where 1/2 is equal to cosine theta. Accordingly, theta equals pi over 3. And that means that this curve I drew in black is theta equals pi over 3. Then, as a reminder, the area formula for polar curves is 1/2 the integral from alpha to beta of r squared d theta, which is somewhat reminiscent to the formula for the area of the circle. And alpha and beta are bounds that are decided in the problem. The first area, which I'm now shading in orange, can be determined by doing the following calculation. Area is 1/2 the integral from 0 to pi over 3, where pi over 3 is the intersection point, of 1/2 squared d theta. This 1/2 corresponding to the radius of 1/2, or the green curve. Expanding the parentheses and pulling out constant terms, we're left with 1/8 the integral from 0 to pi over 3 d theta, which then becomes pi over 24. Next, to find this red area, I'm going to integrate from pi over 3 to pi over 2. And you may ask, why pi over 2? One reason is because, thinking about this blue curve, cosine of pi over 2 is 0, bringing us back to the origin. Another reason that would get you to a very similar place is because pi over 2 is the upper bound of the first quadrant, and we're limiting ourselves to working in the first quadrant for now. So this area is going to be 1/2 times the integral from pi over 3 to pi over 2 of cosine squared theta, d theta. I'm going to apply the power reduction identity for cosine inside the integral, getting us to the following. 1/2 times 1 plus cosine 2 theta, d theta. And I'm again going to apply a constant, leaving us with 1/4 the integral from pi over 3 to pi over 4 of 1 plus cosine 2 theta d theta. Here I'm going to be a little bit informal. Formally speaking, you should consider the integral of cosine 2 theta d theta with a u substitution. Specifically, u is equal to 2 theta and du is 2 d theta. But because this is such a common situation, a lot of people will have it memorized or just do this calculation mentally, which is what I'm doing here. So we're left with 1/4 theta plus 1/2 sine of 2 theta at pi over 2. Oh, I made an error here. This should be pi over 2. And this is going to be pi over 3. In turn, we get 1/4 times pi over 2 plus 0, because at pi over 2 we get sine of pi, which is 0, times half is 0, so we're left with a 0. Minus 1/4 times pi over 3 plus root 3 over 4. Root 3 over 4 coming about because at pi over 3, sine of 2 theta evaluates to sine of 2 pi over 3. Considering our unit circle, sine of 2 pi over 3 is equivalent to sine of pi over 3, combining the idea of reference angles and the fact that our y-coordinate is positive in the second quadrant. And then the 30, 60, 90 triangle, we can see that sine of pi over 3 is square root 3 over 2. Multiplying by a value of half, we get the square root of 3 over 4. So I will be expanding the parentheses and getting pi over 8 minus pi over 12 minus the square root of 3 over 16. This then simplifies to pi over 24 minus the square root of 3 over 16. And combining this with our result from our orange calculation, we get that area is pi over 24 plus pi over 24 minus the square root of 3 over 16. And this becomes pi over 12 minus the square root of 3 over 16. Then, from here, I'm going to consider the area inside the blue circle. You could apply the same integration formula, but that's more work than is strictly necessary. We can see visually that it is a circle of radius 1/2, so considering the formula for the area of a circle, we get that this blue circle here has an area of pi over 4. So then to get the area that in this first diagram is drawn in pink, we're going to do pi over 4 minus 2 times our last results. Area is pi over 4 minus 2 times our last result. As a reminder, we are doing this because we saw that, I should say, the red area plus the orange area is mirrored essentially, right, or symmetric about your x-axis, so that this area down here is the same as the red and the orange area combined. So, expanding our parentheses, we get that this is pi over 4 minus pi over 6 plus the square root of 3 over 8. This then simplifies to pi over 12 plus the square root of 3 over 8, and this is our final result. Meaning that this pink shaded region here for these two particular curves has an area of pi over 12 plus square root 3 over 8. If you found this content informative, please support the channel by liking this video, subscribing, and sharing with friends or family. If you're interested in one-on-one tutoring sessions, please follow the link in the description. Have a great day.